Alright, so today we're going to talk about equilibrium. Alright, so let's say you got a reaction where A plus 2B goes to C. Alright?
Ask them where he's at.
So, when you start off, do you have any products to start with? Before you begin, do you have any products? No. So eventually what happens is these start combining, they make C, and eventually C starts turning back into the reactants. Okay? Now, equilibrium is not great. It does not mean this happens instantaneously, however long it takes to achieve. But once it achieves this equilibrium, these concentrations don't change anymore. They hold steady. All right? What's messed up about it is you may think it's done. Once it's at equilibrium, these A's and B's and these C's stay put. Well, what is happening is these will make C's, and then somewhere else in there, a C will have to go back and make A's and B's. All right? So an equilibrium is dynamic, which means it's always moving back and forth. All right? But the concentrations remain constant. Okay? So, an equilibrium expression is, we're going to write a large K. A large K stands for the equilibrium constant. All right? You have to be careful with this because you have to be disciplined with your K. Because remember, in our last unit, little k stood for the what? The rate constant. This is the equilibrium constant, so this has to be a capital K. All right? This is going to be simply the products over the reactants. Okay? And the messed up part about this is we only care about gases and aqueuses. Thank you. We only care about physical states that are gases or aqueuses. So let's go up here and let's just put a G next to all these. So then we can write our equilibrium expression. So what is this? This is going to be the concentration of C over the concentration of A times the concentration of B, and I'm undisciplined on that side, squared. Okay? What ends up happening is you have to use the numbers, the coefficients out in front become exponents. So this K is unitless. We don't put units on this K. We just ignore them all because you could end up with different exponents in there. You could end up with things to the fifth or no units at all, whatever it may be. All right? So then this equals our K. And we go from there. What do you got, Brian?
Oh, did you just talk about the square being that?
Yep, the square is the coefficient from up here.
Okay, I just missed that.
Yep.
Just
All right. So, if we have a large value, if K is a large number, large value, what side of this reaction is favored? The products, because it's products over. So this means products are favored. Okay? And then of course the opposite is true. If K is small, I'm not going to write a small k, I'm just meaning small number, then the reactants. So that's our value for K. Well, you can also do this for pressures. Sometimes you won't really see this, but sometimes you'll see a little C down here. And the C obviously stands for what? Square brackets, concentration. Well, we can do this for P also. So we can write a Kp expression. And they always put the P. So a Kp is still products over reactants. For basically now until we're done with AP Chem, it's always going to be 1 over what? Products over reactants. The next 3 or 4 chapters are all on equilibrium. Okay? So this would be the pressure of gas C. And then this would be the pressure of gas A, pressure of gas B, still squared, because you still got to use your exponents. Okay? And that's called a Kp. Right. We can link the two together by using this little formula here. Kp equals K times RT to the delta N. And delta N would be the only one we'd have to explain in this, right? The R is the gas law R, so it's the 0.0. This R is 0.0821. It's from our gas law constant. And temperature obviously has to be in what units? Kelvin. So N, yep, N is usually the number of moles. So this is going to be the change in moles. So what this is going to be is it's going to be our gaseous products minus our gas reactants. Okay? So how many gas products do we have? Our example up here. We have 1. How many gas reactants do we have? Be careful, we got to count this one also in here. So we actually have 3. So that means this would be to the -2. Okay? So then you could simply just go in here for this one and write a -2. Right. And if you're better with exponents, a negative exponent really just means it's a what? It's a denominator. It's on the bottom. So if you're doing this like algebra-wise, this would be K over RT squared. This and this are the same thing. Otherwise, you just punch in your calculator, -2, and it does the work for you. So what would happen on this, if I have this number, I can find this, or if I have the Kp, I can find the K. Okay? So,
You forgot the little K.
Come on.
now,
You're on video, let's go.
No flaws.
oh, there's gonna be lots of flaws on here. Okay, it's just like, it's the disappointing thing when I do things on here. When I make a flaw and I erase it, and then I just go, whatever, we'll just leave it on there. Okay, so math with these. So we're gonna have 2 objectives. One is to find K, or 2 is to find our concentrations at equilibrium. Okay? Which means if I have to find K, I have the concentrations. And if I have to find the concentrations, I must have K. Because you can't have 2 variables in our equation that we have. So, let's do the first one. Let's again just keep it nice and simple. We'll do our same reaction. I could pick a real one, but a real one doesn't really matter. Alright? So let's say this is 0.1 molar, this is 0.1 molar, and this is 0.8 molar. Okay? And this was at equilibrium. So again, the first thing you have to do is write a K expression. So K equals concentration of C, concentration of A, concentration of B squared. Right. So then you go through and you plug in your numbers. So I have 0.8 over 0.1 times 0.1 squared. Should be able to solve this one without a calculator. Because dividing by 0.1 is going to make that into what? Goes the other way around. Dividing by 0.1
Just be A.
should be 8. Another one?
No.
Another 0.1?
Another one.
80 and another one?